I will talk about the work we have done in Airbus Crisa with the RISC-V core that we have developed. Airbus Crisa is a subsidiary company of Airbus, 100% owned by Airbus. We are located in Tres Cantos, in the northern area of Madrid, in Spain. We employ about 500 employees, and the business sales, the amount of sales is about 100 million. We have 3 major buildings: design, manufacture, and test. We have, in the 40 years of the company, we have participated in more than 300 missions. We have delivered more than 2,000 flight units. And currently we are working in more than 75 active missions. To name a few, we have worked in Ariane 5, Ariane 6, Vega, the Lunar Gateway, Orion spacecraft, James Webb Space Telescope, the Martian rovers, SpainSat satellite. Getting into subject, we have developed a RISC-V core, hardware architecture, 32-bit data and address space. We have implemented the I, M, and F extensions. We can select which one of them we want to use. We have done an implementation which is single event error protected. We support interrupts, 16 sources plus exceptions. We go to attend them, all of them, to the same address, but we don't support nested traps. We have an interface with the memory, which is tightly coupled with ADAC included and scribing mechanism. We can program in C from Linux, Windows, both open source and proprietary IDE. We can debug by using the JTAG interface and the debug module that we have built in Linux and Windows. The applications that we have built is core for small ICUs with low to mid-range processing power capabilities. And we have built it around a flexible and modular architecture, which was very clear for us from the very beginning. Getting into the architecture, basically, we have a big, or the main component is the RB32 module, where we instantiate the JTAG, the back module, and the core, which implements the instruction extensions that we require. You could use this already in your design, but we instantiate it into what we call configurations. In this picture, you see the microcontroller configuration, where we have included tightly coupled memories, which we connect to the memory interfaces. The tightly coupled memories have EDAC embedded in. We can detect and correct 1 single bit per nibble. We can detect 2 error bits per nibble. And the tightly coupled memories also have an scribing mechanism, automatic scribing mechanism that can be enabled, disabled, or programmed from the software. We have a standard backend interface to connect the tightly coupled memories to the system buses, so we can connect it to APB, AHV, actually whatever bus you would like. So it is completely flexible. Regarding the pipeline of the core, this is pretty standard, but we have built it thinking or considering that the target device is an FPGA. So the main constraint is that the FPGA memories will give you the data when you read, or write the data when you write. In the next clock cycle, after the clock cycle, you emit the address. So everything is built around this. The pipeline supports cache, supports scrubbing for the tightly coupled memory. So when the data is not available, the pipeline knows where to stop or to inject bubbles or do whatever. The debug support logic is controlling as well the pipeline and the interrupt controller as well. These are some figures of performances of our core. We have done some test occupations in a commercial or industrial grade FPGA and FPGA grade device, RTG4. The core where we instantiate the RB32i is really small. It only takes about 2,900 flip-flops and about 70 megahertz. This is with TMR activated. When we include the floating point operations, basically we have about 1,200 flip-flops more due to the register file that requires the F extension. Frequency is not that high, but this figure is already updated. We are reaching higher than 65 megahertz, which is a matter of updating or configuring well the multi-cycle constraints in the synthesis and layout tool, or getting rid of some hazards in the pipe. Okay. When we go to RTG4, figures are a little bit lower in frequency, but this is a much not a light FPGA because of all the rad-hard protections that it has. We have run standard benchmarks, Drystone and CoreMark in hardware at 48 megahertz. These are the figures that we are getting, about 0.78 DMIPS per megahertz and 0.83 CoreMarks per megahertz. Regarding the software development environment, as I said before, we can develop from Linux and Windows. In Linux, we are using the RISC-V GNU toolchain. Basically, in Ubuntu, we support OpenOCD, and we are using the FT2232H board to connect the PC to the hardware in which we are running the core. And in Windows, we are using Seger IDE, which is proprietary C compiler and debugger, but it also has support for the GNU CC compiler. And we are using the J-Link UM08001 adapter. Regarding the verification of the core, we have followed a ECSS FPGA design flow, the one from ESA. We have run the simulation, so the simulation environment is based on open source VHDL verification methodology, which allow us to include functional coverage, random constraint test, and it also allows us to do software and VHDL code simulation, which we already prepared. We have done the verification at different levels. From the unitary point of view, we have run the verifications of the core, JTAG, debug module, TCMs, and the integration level in the microcontroller. We also have tested in hardware the full debugging chain from OpenOCD down to the hardware. And in addition, we took the newer RB32 processor, we put it into hardware and compared with our core from the functional point of view to see that the implementation was properly done, with good results. We have also run the architecture compatibility test for I, M, and F in simulation. They are running fine. And of course, we have run the direct test, the stress test, and constraint random test. We have used this core in 2 projects currently. There are more to come. One of them is this, is in the electrical propulsion domain. The mission is a few years. We have instantiated the core into a industrial grade FPGA, which needs a rad-hard companion FPGA monitoring this. If there is something wrong because of radiation, this rad-hard device can restart this. The architecture runs about an IPv bus because we don't need to transfer many data. Regarding the software, we have some drivers class A and bare metal application class B. The initialization block is able to go to the flash, gets the images of the software images and load it into the device, into the processor config memory, and then it handles control to it. And in addition, we have the services block with timers, watchdog, and the sources of interrupts. And the other processor and the other application, sorry, where we have used the processor is also in the thruster domain, liquid propulsion precisely. The mission time in this case is about several hours, so we don't need a rad-hard companion FPGA to monitor this device. The software stack is a bit more complicated. In this case, we have drivers, class A, some boot software, class A, and application, also class A. We have the initialization block like before. It's loading the boot software, and then the boot software is in charge of completing the full load of the application. And basically, this is all we wanted to share with you. So thank you.